some sense that you might not know exactly what you're supposed to be doing. So I'm happy to respond to that. And then 6 weeks from today is the complete first draft of the research proposal in toto, no more than 6 pages, I think. I have more details in the syllabus. But we're still learning today and Thursday about techniques for going after causal data, specifically instrumental variables. So any questions about deadlines or any kind of class mechanics stuff? Okay.
So the proposal, Andy, that's just...
I'm sorry?
The thing today, that's just the question and the data.
Yeah, it should not take you more than really a paragraph. Potentially it could be 2 sentences. Some semblance of just, you're putting a stake in the ground. It's not binding. You can change your mind. I won't be surprised if you fine-tune it at least. I won't be surprised if some of you completely revamp it between now and when it's due. But at least you've been forced to think about it enough to say, here's some questions. And I'm interested in answering with some data sets that might actually exist in the context of the proposal. All right. So what are we talking about today? So first I want to take stock. Last week was a little bumpy, I think, in terms of fixed effects and first differences, and some of that may have gotten too much into the weeds. I want to pull back very briefly and give a sense of where we are with the techniques that we've covered, and then launch into what I think today will be entirely conceptual. I hope by the end of the day that you have an appreciation for and some conceptual understanding of how to, or what an instrumental variable analysis is and what its benefits are, and even start to see how you might go after it. On Thursday, I'll talk more about implementation in Stata in general using a technique called two-stage least squares, but we're not there yet. First, you have to understand what an instrumental variable is. So first, even before that, let's take stock and go back to our first set of methods was all around the theme of controlling for observables. So we talked about regression, matching, and propensity score adjustment. And propensity score had a whole subset of different approaches to using it: stratification, matching, even including propensity score in a regression type model. But they're all doing the same thing in slightly different ways. They're controlling for things that we can control for. And so if we want to be able to say at the end of our regression analysis that the coefficient on our treatment covariate of interest is causal, we need to appeal to the conditional independence assumption. We need to say that everything that matters is in the model. And if that's not true, then we don't have causal estimates. And if it is true, then we can. Now, nothing prevents you from appealing to the causal, the CIA, the conditional independence assumption, whenever you want to. But that doesn't mean that just because you can that it's right. And so this is becomes an argument. And so generally it's fairly dangerous business unless you're quite confident that that you do have everything in the model that belongs in the model, that then that your estimates are causal. And so, the same thing, we can say the same thing in a different way and say that everything that is in the model should be in the model. In other words, nothing that's not in the model, nothing that should be controlled for is missing from the model. And also, that has to deal with one of our 3 types of threats to inference related to omitted variables bias. But there are also potential for reverse causality, that X causes Y, but also there's another direction, Y causes X as well. Controlling for covariance won't deal with reverse causality. It also won't deal with this other relatively less important threat called measurement error that we've talked a little bit about. It won't handle those. It's primarily a story about controlling for the appropriate variables and making sure we don't have any omitted variables bias. Oh, yeah, Liz.
So I still can't quite understand what a propensity score adds in addition to all the other things you're controlling for.
In and of itself, it doesn't add anything. It's just a summary.
Why do you need a summary? Because if, let's say you like plug in all the other things, right?
Right.
Why a summary?
Well, so in one particular case, it may be that you want to control for a lot of things. Say you want to control for 100 variables. You don't have enough sample size to control for all of them at once, because you need at least as many observations as you have variables, and in reality you need something like need being a loose word, you get something like 10 observations per covariate. So if you've got a really wide data set, but not a very tall data set, I guess, then propensity score can get you out of a jam by summarizing that data.
Got it.
But that's not the only reason why you might do it too, right? So another application of propensity score is to match. And so you can take the regression, you can take the propensity score and say, okay, I really want to focus my analysis on the subset of individuals who, in the counterfactual, would have gotten the treatment but didn't based on the observable characteristics.
Mm-hmm.
You can do that with propensity score. You can also do it with direct covariate matching.
Right.
You can't really. Regression does it for you, but in a less elegant and less potentially precise way because you're including everybody in the data set regardless of what their likelihood was of getting the, say, treatment that they, in the counterfactual group they didn't get.
Yeah, I mean, I guess you look at the table 1 or whatever, right, and you're like, okay, half of them are 72, and so is the other half, blah, blah, blah.
Blah, blah, blah. Right?
Yeah, so so like you eyeball it for matching, theoretically, right? I guess I'm trying to, if you were studying about trying to see cause and effect, and you needed to find a control group, then I guess if you were hunting, like, for instance, well, I've just been trying to read all these things about this, and like, so if you were studying like Medicaid expansion in 3 states and you wanted to find 3 other states that were, would that be a setting where like a propensity score would allow you a better match than?
Well, you might think it's actually pretty hard to propensity score match at the state level.
Oh.
But the concept is the same, right? I mean, again, it goes back to this idea of the counterfactual. So we can observe the people who got treated.
Mm-hmm.
We want to see what their experience would have been in the alternate universe where they themselves did not get treated.
Uh-huh.
So we want to find controls that are as close to, essentially identical to those
Right.
who did get treated, right? So what regression is doing is saying, okay, well, let me control for those observable characteristics. What propensity score is saying, let me either control for those observable characteristics, or let me find you a subset of the control, the sample of eligible controls that are most like the actual treatment group. And so they're, at the end of the day, though, it's all about controlling for things that we can observe. We have to have the variable, the covariate of interest, to be able to either control for it or match on it.
Okay. Yeah.
Okay?
Yeah.
Any other? So, we've covered this. I hope at this point none of this is surprising to you. If you have any questions about this, lay them on me. But conceptually, this is what we're doing with these set of methods with regression and matching and propensity score stuff. Okay, so then we turned it up a notch and went after discussed methods, or I discussed methods about controlling for time invariant factors. So these include first differences and fixed effects type analyses. The key thing here is that now we require longitudinal data, panel data. Where we're now, the key innovation here is that we're using each subject as its own control. So any characteristic of the subject that doesn't change over time, by construction falls out. You're comparing yourself now to yourself in the past. If your hair color didn't change, and if it didn't change, how could it affect the outcome? It can't, so it falls out of the model. Now, it's important here to realize, too, that difference in differences and triple differences are specific examples, specific applications of the first difference or first effects approach. They don't necessarily require panel data themselves, because we can do it with repeated cross-sections, but realize that we're looking at something, the same something over time, maybe the same states from pre to post, even if the sample respondents from our survey are changing over time. So what this gets us automatically is, especially in the panel data context specifically, it gets us the ability to say time invariant characteristics are controlled for regardless of whether or not we can observe them. We can observe some time invariant characteristics and we can control for them in a regression model, but we can't necessarily observe all of them. If we're worried about time invariant characteristics, baseline differences that might affect treatment, if they're time invariant, we can control for them automatically. But if we want to say our results are causal, we still have to appeal to the conditional independence assumption but it's a narrower appeal. We're saying now that for our estimates to be causal, we need to assume that all time-varying characteristics, specifically the ones that potentially influence both treatment and outcomes, are controlled for. So even with the fixed effects of first differences model, we still may want to add covariates to the model specification. We can do that straightforwardly. We're expanding regression. We're saying, okay, we're controlling for things that vary over time, and we're also controlling for time invariant characteristics implicitly in our design now, or explicitly by adding a fixed effect, say. But we're making this critical assumption to say, if the coefficient on this treatment variable is causal, it's because every time-varying characteristics that we need to control for, we are controlling for. It's a smaller list of things, potentially, although it may still be infinite, but it's still embedded in this concept of regression control, right? We're just controlling for different. The trick here is using the subject as its own control means time-varying characteristics fall out. We're controlling for them, they go away, we're not worried about them. Talk about this, hopefully this is consistent with your understanding from last week, more or less. This is the conceptual, everyone ought to be at least on this page, I think, so if you're not on this page, you have questions about first differences or fixed effects, we can talk about them. All right, so then let's jump into the final frontier. Some common limitations so far. All of these, or both of these sets of approaches require some appeal to the conditional independence assumption to get around the potential omitted variables bias. And neither of these sets of approaches address these other two lingering threats to inference. The reverse causality, again, Y may have a causal relationship with X, even if X also causes Y, and the potential for measurement error. So regression control, density scores, first differences, fixed effects, diff and diff, triple difference are all stories about omitted, kind of addressing omitted variables bias, but not doing anything about reverse causality. But all is not lost. There is a way. There's a way I want to talk about today called instrumental variables that will address all these things, but nothing is free, of course. And it turns out that instrumental variables is kind of this double-edged sword. It promises to give us causal estimates even in a cross-sectional data setup, but it's technically complicated, potentially. It's even a little bit conceptually complicated, which is what I want to spend today talking about. And it also can be a big pain in the ass, which means that you spend a lot of time arguing about whether your instrument is a good one, and then also undertaking a variety of statistical and kind of procedures to try to make the argument that, in fact, your instrument has a good set of properties that makes it a good thing. So it's kind of in some ways, it's kind of a full employment act for economists and methods people. But it's not fool's gold, but it is very shiny. And so we need to be careful. But let's understand what it is before I get too excited about, or knock it down too far. So, instrumental variable is some third variable, we'll call it Z, that serves to pseudo-randomize the assignment of some treatment, I'm calling X here. It has to satisfy at least these two conditions. In fact, at the end of the class, I'll talk about the 5 total conditions that an IB has to satisfy. But the first condition is relevance. That is, this third variable's instrument Z has to be positively, or not positively, but has to be significantly or sizably, substantially correlated with the treatment variable itself. It has to influence whether or not you get treated. But the exogeneity requirement, we'll go into these things more in detail, assures that the correlation between the Z, the instrument, and the error term E is itself 0. The implication of that is that Z, the instrument, has to be uncorrelated with Y, conditional on X, and it can only be correlated Y through X itself. So basically what we're saying, and I'll say this a variety of ways over on, going forward, is this instrument has to influence whether or not you get the treatment, but can't otherwise influence your outcome except through this treatment. So this is a pseudo-randomizer. It's not random assignment per se because we're going ex post and finding this variable after the fact, but we're going to, I'll lay out today how we get that.
That calf distance example, would that meet those requirements?
We'll talk about that exactly in a little bit.
Okay.
So you're going to give an example?
Yes, I'll give examples, yes. This is Jay, setting the stage and trying to confuse you. So let's try it again with my mad PowerPoint skills. If you can understand that with that first glance, then you're ready to teach the class. Over here is our outcome y. In some treatment variable x, I put the double arrow here to say that maybe reverse causality, right? X may cause y may cause x. There's also this variable w that influences both x and y. If we're not controlling for it, then what is it? It's an omitted variable, right? And our estimate of x and y is binary. Even if we are controlling for w, because of this reverse causality, our estimate of the simple effect of x on y, not accounting for this reverse causality, is going to be flawed.
I'm sorry, reverse causality is just the effect that y has on x.
Simultaneous causality, right? So health status and insurance might cause each other, right? You have to, yeah. Our hero, Z, lurking out here up in the corner, is drawn in a way to hopefully understand that Z influences X. It doesn't have any direct or any other effect on Y except via X. That's the big Ghostbusters through the middle right there, right? And so what it does is it allows us to get the single unidirectional causal effect of X on Y, even though we may have reverse causality, and we may also have omitted variables bias at the same time.
That's really bad.
I'm sorry?
See what Tim drew, the little circles over there? Is that the exact same thing as what he was saying?
I have no idea.
No, let me ask you, because what he was showing is, because you use the Venn diagrams too sometimes. So the bottom circle would be Z, and the top circle would be Y. So Z is totally independent of Y, but Z affects X, which affects what, right? So is that exactly, because we were just trying to learn this concept from a different angle, so I was just trying to figure out if it's the same thing.
What's he talking about? Well, it looks like it's...
So much suppression.
Yeah.
Yeah. Is that not the same thing? Okay.
Is Z then like a mediator?
No. Z is not on the causal pathway between X and Y. Z is, think about, well, I'll show you, I'll start talking about some examples, but yeah. Z should influence X, but not influence Y. Whether it influences...
Except through X.
Well, right, it doesn't have any other mechanism any other plausible mechanism to affect Y except via X.
So essentially Z should be some marker of X that Y and W have absolutely nothing to do with.
Well, Y has something to do with it because it's affected by X. It's this pathway right here. Z is only working through X, and because Z is only working through X, by assumption then we're able to pull out the causal effect.
Okay.
But does Z completely explain X's effect on Y?
Does it explain X's effect on Y?
Is it?
Well, it can't be perfectly correlated with X, right? It'll have the same problem, so it's going to be partially correlated with X. This is where we get into the art. Instrument variables is as much an art as it is a science. But let me start getting into something. Let me go work through an example and see if it makes sense conceptually too. Well, actually, let's show you some more diagrams before we get to the example. But any questions about this version of the diagram?
Just one quick.
Sure.
Does putting Z into this equation, does that have any effect on W? Does that explain W or?
Z should not be correlated with W, right?
Okay.
Z should only be working POW through X. Okay.
But it has nothing to do with W.
It shouldn't, right? Because if it has something to do with W, then it's violating my assumption that it's
I guess I'm reading
working on
why
Y.
we're putting Z in that.
Well, why we're putting Z? We're not going to be putting Z into the equation per se. We're using Z as a way to exogenously shift the value of X without affecting anything else. So we need to get, the problem right here is X, without Z, X is, X is contaminated, right? X, our measure of X is big, we don't have W, and we may have reverse causality here too, so it's no good. We're trying to purge X of these other influences to get just this pathway right here. Z is going to work to basically shift X for us.
What is the red arrow that's drawn?
That's what you get at the end is the causal effect of sigma.
Okay, I'm
It's kind of hard to draw, right?
The blue one that goes both ways is the association, the correlation.
Right, it's the reverse causality, and this is at the end of the day, this is what we're left with if we do it right.
Perfect. Okay. Great.
So you want to try to figure out the red arrow, which is the
Yes.
effect of X on Y
The causal effect of X on Y.
without the impact of what Y may have on X and what W may have on X.
Right,
Okay.
right.
Okay.
We're trying to, it's our silver bullet. If we have this Z out there, we can approximate a randomized controlled trial, in theory, and get rid of all this stuff, even though we have secondary data. Yeah, Tori.
Why does the Z get rid of the reverse causality?
Because it's outside, so it's not, Z is not affected by Y. So we're using Z to say, okay, as Z goes up, X goes up. So we're what's called exogenously influencing X. We're moving X in a way that is unimpacted by Y. And I'm doing it by hand waving in pictures now. But as a result of that, we're saying, okay, we can move X exogenously and then see how Y varies without worrying about the reverse causality in that case.
Also, showing us that.
So in terms of distinguishing Z from a typical compounder, the primary difference is it only affects X as opposed to affecting X and Y, right?
Now we use your typical compounder.
Okay, gotcha.
We want Z to not be correlated with any confounders. We want Z to just be this narrow channel of
To
light,
the trees.
lasering in onto the treatment,
Got it.
but not otherwise influencing anything else in the system. Okay, so I'll try and show it to you in a slightly different diagram, but hopefully it just serves to reinforce. Initially, we have this situation where we have some X and Y. So this is back to the Valentine diagram where we have sort of the circles represent the variation in each of the variables. X is our treatment, Y is our outcome. Y kind of consists partly of sort of Y hat over here, which I didn't draw, and the error term E. Right? And so the basic problem is that in the beginning, X is correlated with Y. Part of that correlation overlaps with E, violating our mean independence assumption that X and E are correlated. In other words, we have omitted variables bias. Right? We have this potential correlated variables, or actually potentially could be reverse causality as well. We're different picture, same story. We've got problems here. We've got the potential where X is being influenced by some outside confounder that's not controlled. So Z comes in, and maybe this is the closer analog to Tim's diagram, although I'm not sure. There may be some key difference. I think there may be a key difference, although that's not really the point here. We're going to use Z, the variation in Z, to get at, basically to isolate the part of the correlation where X and Y overlap that's pure of the error term. So it's only going to be this part that's, I drew this obviously on purpose, so it's not like you can just draw whatever diagram you want to. But if Z is working the right way, it's correlated with X, purifying the contaminated part of X that is correlated with the error term to isolate the causal impact of X through this little, right here, pushing E off to the side. That's what's going on conceptually. It's the same version it's a different version of the same way here. Depends which one you like better. Again, Z focusing in on X to get the unidirectional causal effect of X on Y by purging X of the influences of these other.
But in your diagram, Z is overlapping
With Y, and they're not independent.
in this
That
one.
makes sense.
So,
Well, they have to be but so.
but it's not in your.
I'm sorry.
But it's not in
The first
in
one.
the other one.
No, but so this is a correlation.
Right.
They're different. It's not that they're
Okay,
overlapping. It's just that the important thing to understand is the only way Z does have an impact on Y. If you look at the unadjusted, not controlling for X impact, right, it has to have an impact because it's working through X. But so there is a correlation between them, but the correlation conceptually can only occur via the pathway from Z to X and X to Y.
Okay.
So that's why they do have to be correlated here.
Right.
Because if they weren't correlated, then there wouldn't be any, they'd be
Okay.
uncorrelated.
They're independent. Okay.
but it's only working through. The only way, so the way I drew it, I actually was pretty careful about this. The only way they're correlated is the shared correlation that Z, every part of Z that overlaps with Y is included in the portion of X that's overlapping with Y. So we're using a subset of this pure correlation. Ideally, we would use green plus purple, but we can't be so lucky as to say there's a magical instrument that guarantees we'll get green plus purple. So we'll settle for purple because purple is less than what we want, but importantly, it doesn't include red, and red is bad. Okay. So let's walk through a version of the cap distance example. So, a research question. Does more intensive treatment improve patient outcomes? That's a causal question. That is, does actually getting the treatment cause better outcomes? Let me offer some stylized facts. Stylized fact 1, patients who receive more intensive treatment are more likely to live. This is not supposed to be clinically specific or anything, it's just a stylized fact in a hypothetical example. So if we saw this pattern in the data, what would we conclude? Would we conclude that intensive treatment therefore saves lives? And would we conclude that patients who are selected for intensive treatment are somehow healthier than those who aren't? So if we could control for their baseline health in a comprehensive fashion, we don't need instrumental variables. We could add all the risk adjusters to the model that we have, and then say, appealing to the conditional independence assumption, we've controlled for everything we need to control for. Everyone, once we control for all these risk factors that we have, treatment assignment is effectively random at that point, and we don't need instrumental variables. But can we ever be sure that we have control for all the possible risk factors that are out there? Arguably no, right? And so we don't know whether it's this is reflective of a direct causal effect or whether there's selection bias going on here where patients are different. Patients who get the treatment versus patients who don't are somehow different in ways that are uncontrolled for and are kind of affect their mortality outcome.
I don't understand an example what the reverse causality would be.
Oh, I didn't say there wasn't any reverse causality. This is just a variables bias I'm talking about.
Oh, you're
here.
starting to, okay, go ahead.
Yeah, but so that's cool with the setup, right? Pretty standard setup. Okay, so let me offer 2 more stylized facts. Patients who live closer to centers with more intensive treatment options are more likely to get intensive treatment. That's something we can test in the data, and I'm just saying I'm asserting it to be true for the purposes of this example. We also see in our data that patients who live closer to centers with intensive treatment options are more likely to live. Okay? So the question then is, does where a patient live, directly influence whether the patient lives? So is there something about where you live, if you live closer to a hospital with intensive treatment options than not, or the people who live farther away, are you somehow different in your underlying risk profile? Are you somehow different in ways does that have a causal impact, or even is that correlated with something else that might affect your risk of living, your mortality outcome? Because if not, then the only way to explain the lower mortality rates is to say patients who live closer to centers with more intensive treatment options are more likely to get those intensive treatment options and therefore more likely to live. So we're using that, if this assumption is okay, we're using this distance away from how far you live to a hospital center with a treatment as a way to effectively randomize patients into whether or not they get the treatment. Patients who live closer, well, they get the treatment, but not otherwise different. That's the assumption, that's the assertion we have to believe for us to be able to use distance as an instrument for treatment assignment in this particular case.
So you're trying to figure out whether distance is the typical confounder type or whether it's W or Z. Right.
Right. So I'm setting up a Z, right? I'm saying but you're saying could it be? But the other question is we're starting off with, is it Z, right?
Is it Z or is it W?
But, right, and so if we can say, like, there's a story that says, well, actually, there is something about living closer, like, let's say...
I have an example that I was just thinking of,
Okay.
which is that, because I thought you were setting it up to be W. So my example would be that urban versus rural. People who are urban are more likely to be other things that aren't just closer to a treatment center. So people that are urban are more likely to be close to a treatment center, so it affects the right, but the one that it affects the distance.
So that's true, right.
For the
Distance
treatment.
affects, right.
But it also affects directly whether you live or not, because whether you're rural versus urban has like a million other effects.
Okay.
So I thought it was W.
Okay, no, that's a great example, right? So if we took it too far, we might find that that this distance has, that story that you're telling makes total sense. What if I narrowed it in and said something like, in Metro New York, people live in different zip codes and hospitals are arranged around the city, and, you could measure it down to the hundreds of feet or whatever and say people who just physically live closest to the hospital, comparing people who live a mile away versus people who live 5 miles away. Is that enough distance for us to think people who live differential distance are going to be somehow different in characteristics that affect their outcomes, as opposed to just different in their likelihood of getting the treatment because they live closer or farther away to a hospital with, an intensive treatment center. So context totally matters here, right? Like we could say urban versus rural. We could say, what about something like cancer, right? Like cancers are chronic diagnosis when you have a long time. You might think there might be some time for adjustment on the part of patients to move. So in fact, yes, like I have a chronic disease, there's a reasonable likelihood I'll need an intensive treatment. I'm going to move so that whenever there's a case that I need this treatment, I'll be right across the bridge from this hospital. Then this isn't working anymore, right? This story isn't working. On the other hand, what if I think the most famous example in this particular setup is, what about a heart attack, right? Relatively, I would say it's not unpredictable, but it's relatively unpredictable. Most people don't know exactly when they're going to have a heart attack. And certainly we might think it's plausible to say people aren't going to be moving closer to centers with cardiac cath capacity because they think they might be having a heart attack, right? So where you live is probably exogenous to whether or not you're going to get, in the case of the McCollum paper or the Stuckel paper, we're going to read next time maybe, you have a heart attack, where you live affects how far you are from the hospital, affects whether you're going to go to the hospital that has the treatment versus not, but isn't going to otherwise affect whether you live or die once you start down that path.
Right. Okay. So I'm just trying to very basically understand the steps you're going through, and so I think I don't have to think of a good example, but all I need to know is that what you're doing is trying to figure out what are your W's, your co-founders, and what are, I don't know what you call that Z thing, what are your
instruments.
Thank you, instruments. And so as you go through them, you are thinking at every step, does this affect, is there any possible way that this could affect directly without, and I can't come up with a good one, but you're trying, but I just...
It goes back to the diagram. If at the end of the day you understand nothing else with the diagram, it goes back to this. If you can say a good instrument has to be sizably correlated with X, but not influencing the outcome otherwise. Does distance from the center mean this metric? I mean, so you see, this isn't a statistical story anymore. I mean, it'll turn out we can test, we can observe this, right? We can observe how well correlated these two things are, Z and X, because we have data on both of them. How do we tell whether Z is going to be otherwise affecting Y? Stata can't tell us that. Regression can't tell us that. Statistics and econometrics can't tell us any of that stuff. It becomes a story about, this is my instrument, this is, it's strongly correlated with X, and this is the argument about why it's, not otherwise affecting my outcome. And so conceptually that's where the art is. If you're proposing to do an instrumental variables analysis, it all is predicated on your ability to be able to say, I've got a good Z. I've got a good instrument that's going to do what I want it to do. Or more than one instrument is even better, that you can try it a couple different ways effectively and see how it goes. All right, so okay, so again, sorry.
No, I just laughed because you're funny.
Oh, thanks. All right. Well, anyway, back to instrument variables. All right, so I think we can cover it this way. So, all right, so let me just walk you through the rest of the example, which we've basically gotten. We know people who live closer to the center with intensive treatment options are more likely to get that intensive treatment option. That's one of our stylized facts. We know that people who live closer to the center with the intensive treatment option are also more likely to have better outcomes. That's one of our stylized facts. But we're assuming now that people who live closer to the center with the intensive treatment option are not necessarily have better outcomes after controlling for treatment type. Same thing as saying that there's no residual effect of the instrument on the outcome after we control for whether you got the cardiac cath or not, or whether you got the intensive treatment or not. It's all through the effective distance, or distance to the center, is all through whether or not you get that treatment. If you can say that confidently, or you can convince people plausibly, then you might be in business for an instrument variable. And then from that logic, you're then able to conclude, therefore, people with intensive treatment get better outcomes. So I just made that conclusion. Again, the identification comes from these two assumptions. Proximity to center with the intensive treatment, that is what we're calling the instrument. Distance, the proximity affects the receipt of the intensive treatment, whether you get it or not, but does not otherwise affect patient outcomes. If either of these assumptions are not accurate, then your results are not going to be causal. So you have a pretty high bar here. One of them's testable, one of them's a story about hand waving, which is what makes life fun. Like, all of a sudden it's not, simply a data story, it's a rhetoric story. And, probably it's like one of the things where a good instrument is on its face a good instrument, and people generally don't disagree, even though as soon as you read a paper or submit a paper that has this instrument variables analysis approach, the game instantly becomes, let me think of the ways why this instrument is not valid. That's, so if you're a reviewer and someone says IV, you say, what are the mechanisms is this instrument working through to affect the outcome? If you're a author and you're using instrument variables, you say, what are the potential outcomes, what are the potential pathways that this instrument might be working through, and how can I present evidence or arguments that would suggest that those are in fact not pathways we are concerned about. By and large, there's no perfect instrument, so even if you think your instrument is perfect, someone's going to say, well, because if you're in the land of instrument variables, you're in the land of arguing about whether or not your instrument is a good and plausible one. So let me show you an example of instrument variables in the context of randomized controlled trials. We haven't talked about RCTs much, except as to use them as a good comparison group. But it turns out that there may be reasons why we want to actually use an instrument variable analysis, even if we're doing an RCT ourselves. So let's suppose we have a standard two-arm RCT setup that is treatment versus control. People get randomized ahead of time, right? We've already talked about this when we're setting up our conditional independence assumption and showing that randomization gets rid of the concern of omitted variables, right? Because by randomizing, now all the treatment and control are in expectation equivalent to each other. But what if we had one-sided noncompliance? What if we had a situation where you offer the people, okay, you've been randomized, you're in my trial, you've been randomized to get treatment, would you like to participate in the trial and get treatment? You can say no. You can not comply, or you can say yes and then still not comply, right? You can say, okay, I'll be in your trial, but I'm bailing out. So some of the people assigned to treatment might actually wind up being untreated. In contrast, if you're randomized to not getting treatment, then you don't have access to treatment because you're already in effectively the loser's bracket, and you can't go back, you can't cross over. So that's what I mean by one-sided compliance, okay? So normally how would we analyze these data? We probably use something called intention to treat analysis.
But I'm sorry, I don't understand that example. The one you just gave.
The one-sided non-compliance?
Yeah, I don't get it. Because if it's blind, then the patients don't know if they're. Because I just don't understand how that wouldn't be.
Well, it might not be blind, right? So.
Would it?
I'm just talking about a generic example of a situation where.
Got it. The effect, whether or not you get it, depends whether or not you get it.
You can be randomized to 2 arms, right? So I mean, you start off here and you get, assigned treatment or assigned control. Control's an absorbing state, right? You can't leave control. You can never get treatment. But some of the intended to treat could actually deviate and not comply with the treatment protocol and just say they're not getting the treatment.
Okay.
But it's up to them to decide that. But it's literally one side.
I understand. Thank you.
Okay, good. All right, so how would we analyze these data? Intention to treat, right? We'd say, all right, we don't know what their actual, or we might know, but we're not going to be concerned about we're concerned about it, but we can't do anything about it. We have this non-compliance. We're just going to analyze the data based on what your assignation was. Were you assigned to treatment, whether or not you actually got treated, versus were you assigned to control? Because that's what the randomization is based on. Okay? That's our typical intention to treat setup. But intention to treat is nice. It gives us a causal estimate of what? It gives us a causal estimate of the effect of offering treatment, right? It's not the causal effect of actually getting treatment because you have non-compliance and there's going to be this selective or selection bias in terms of people who are deviating, the non-compliers in the treatment arm, who are going effectively to the control arm. In fact, we would expect that usually the people who actually get treatment tend to be healthier and that the intention to treat estimate of the treatment is a lower bound of what the actual effect of the treatment on the treated is. Because we have people who are deviating are probably going to be less healthy on average to head down to the control arm. But here's where variables comes in. We can use the random assignment at the very beginning of the trial as an instrument for whether or not you got the control, whether or not you got the treatment. So we have this perfect variable, right? It's Z. The assignment is Z. It is saying Z affects whether or not you get treatment versus control, but it's randomly assigned, so it can't possibly affect your outcome any other way except through whether you got treatment or control. And in that way, we can use Z to isolate the causal effect of the average effect of the treatment on the treated, in contrast to the intention to treat analysis. I'll show you more about that in a second.
Again?
The instrument.
Okay.
So out here we have the assignation, right? And so some of these people are going to stay in treatment and some of them aren't. But we could say assignment influences treatment status, but then here's outcomes. But does it influence outcomes? Does your random assignment influence your outcome? Only through the treatment, right? How can we know it can't?
Because of the random.
Because it was randomly assigned.
Thank you. Got it.
So Z meets our criteria as in fact, well, in this one case, it's got a perfect instrument. It's a randomly assigned feature about the person that affects whether or not they get the treatment, but doesn't have any impact on what their outcomes are except through that channel of treatment.
Is that what's being done when you read that something is an as treated analysis, or that's different? You have to get it an as treated analysis.
Oh, yeah. So that's what I mean. I'll show you more detail. So we want to actually get the causal effect of the treatment on the treated,
right,
not the causal effect of offering treatment. I mean, both may be of interest depending on the situation. But if you want a causal effect of treatment on treated in a situation where you've got this one-sided non-compliance, you can use the random assignment to instrument for whether or not you actually got the treatment.
Are you going to give an example of that?
What do you mean?
Like a clinic. I mean, all I can think about is like distance from cat, because that's all I can understand. So.
Well, I'm sure you would say more than that.
No, but it's like it makes sense to my world. So I could never randomly assign a patient to live in a rural area, and then. I don't understand this idea of a random assignment also.
Well, I'm saying this is a particular application of instrumental variables. If you some of you may understand everything, some of you, so distance to cat is something that exists in the world, like distance to treatment, is something that we could get from secondary data.
Right.
We can't get random assignment from secondary data, but we still might use, regardless, treatment randomization or randomization to arm is an instrumental variable for whether or not you got treatment. It may not be applicable to the case of whether or not you got cardiac cath or not, because it's not, I mean, you have to do this, you have to have the actual RCT to analyze.
So you can only use it for the variables that you can randomize. You can't use it for the one that she gave because.
What is, no. So they're both, I mean, at the end of the day, it's a story about trying to find instruments, Z.
Okay.
We're trying to find where these instruments come from. I'll talk a little bit about it at the end, but one place they may come from is differential distance to treatment kind of stuff, right? Another place they may come from is if you're analyzing an RCT, you have the capacity that you have an instrument built into that whole setup. We're not analyzing RCTs in class, but I still wanted to use this example as it's a great application of instrumental variables because you've got this rare situation where you've got a purely random instrument that only affects treatment and doesn't affect outcomes. Whether or not you can actually use this in your particular setting is going to depend on whether or not you're analyzing RCT or not. So again, to do an instrumental variable analysis, you have to have an instrument. There's no such thing as the instrument store. I mean, there's really only like, what's everyone else done? And then potentially, wow, I have this brand new idea for a really cool instrument. Maybe I should do something with it.
So I guess in this example, you would set your data analysis up with intention to treat. That would be how you would like set everything up. But you might use this if on one arm more people didn't take the treatment because I guess I'm just confused about the setup because I haven't really seen this done. Like I'm used to mostly studies designed with that from the outset of intention to treat. Is this something you're doing like when you've collected the data, you're just trying to analyze it a different way?
No. You can take a trial. Let's say there was a trial that existed in 1995.
Yeah.
And they had one-sided noncompliance.
Right.
And they reported the intention to treat.
Right.
You could go and say, first author or corresponding author, dude, I really want to analyze your data.
Right.
And I need to know, to analyze your data, I need to know what treatment assignment there was, like who was assigned to which treatment and what their outcome was. And whether they actually got treated. I need those three things. What your assignment was, whether you got treated versus control, and what your outcome was.
Yeah.
And then I can do an instrumental variables analysis based on that gets me estimates a different parameter. It estimates the effect of the treatment on the treated, not intention to treat.
Right. So it might make your data look better.
Well, it's an alternative.
It's an alternative. It's an alternative.
It reveals a different piece of information.
Parse out a
There's
different
papers
group.
that I've been reviewing that do both. They have like
Right, they
intention to
do
treat
both.
and then they say an as.
And then they did,
analysis.
because that's the way I'm used to.
But so if you do a normal, if you do an as treated analysis, right? If you're doing that in the context of you have, so if you just do simply, if you take these data and say, okay, let me just compare treated and control, right? You've got selection bias if you've got this non-compliance issue.
Right.
And if all you do is just compare the two, and you're saying, okay, well, I can't do anything about it, you're ignoring the fact, well, you're not ignoring the fact, you may not know the fact, that you can actually do an instrumental variable analysis to get a more precise estimate of the causal impact of treatment on treated. In the context of a one-sided, I'm not saying, like, this is not a class about RCTs, I'm not saying this is anything you should go out and do. What I was hoping to do with this example is to demonstrate, I'll give you an example of a genuine instrument that, an example of an instrument that could be quite useful even in a kind of unusual setting as an RCT. But in this particular case where you've got one-sided and non-compliant. It's not going to be, anyone working with secondary data, unless it's from a trial, is not going to be able to use this specific instrument probably, but might want to look at something. This is an awesome example of an instrument. They were randomly assigned whether they got the treatment, and so those kinds of things that might be out there, like distance to facility, the kind of thing that effectively randomizes you to whether or not you got cardiac cath or not. If it is, boom, you're in instrumental variables land. If it's not, then it's a confounder, maybe you need a control for it, or it's just a flash in the pan and move along, there's nothing to see here kind of thing. So, how do we, I mean, we can actually do, just to go back to this RCT thing for a second, we can actually do this analysis really easily, even without any covariance. So we know your outcome Y, this is the mean of the outcome for those who got, who were assigned to treatment, and the difference of that and the mean of the outcome for those who were assigned to control, right? If we just do that, that is our intention to treat analysis, right? So the instrumental variable analysis is simply saying, okay, let's take this one step further and let's control for non-compliance. Let's divide by, this is the formula, I'm not saying this is not coincidence, this is specific, this is intentional, but the formula is to say, okay, let's divide then by the difference in compliance conditional on being assigned to getting treatment minus compliance conditional on assigned to not getting treatment. In the assumption of one-sided non-compliance, right, this will be 0 because everybody who got the control had to stay in and never could get the treatment, so everybody complied with being controlled. And over here it's going to be, if it's perfect, if there's perfect compliance, then we don't need IV. We have an RCT, and intention to treat equals the IV, and away we go. If by assumption we don't have perfect compliance, so that some of these guys deviate, and this T bar is less than 1, the compliance rate is less than 1 in the treatment arm, then we could divide by it, and we're now getting the causal impact of our treatment, the effect of the treatment on the treated. Cool? Cool, all right. So, again, the identification assumption here is that the treatment assignment is assumed to influence outcomes only indirectly, specifically via whether or not you get the treatment and not through any other pathway. And then the other question that's important here is, who is this interpretation, who is this IV effect, IV estimate of the effect of the treatment on the treated? For whom is this an unbiased causal estimate? And the answer is that it's at least true for the so-called marginal patient. Those for whom a change in treatment assignment would affect whether they actually got the treatment. That's going to be an important caveat or condition or a fundamental feature of instrumental variables, that you're identifying a treatment effect for what's called the marginal patient. So in the context of distance, we're identifying, like we said, like, okay, well, we have this effect of the differential distance to the closest facility that has intensive treatment versus not. We're saying that's our instrumental variable. If we use that approach, use distance as an instrument for whether or not you got treatment, we're going to be identifying the effect of getting the treatment, specifically for those people who would, those so-called marginal patients, who would change their treatment if they moved closer or farther away from the facility. So there's some people who are always going to get capped. There's some people who are never going to get capped. And then there's a subset of those people who, depending on how far away they live from the hospital, are either going to get capped if they live close, and as they get farther away and across the threshold, they're not going to get capped anymore. Those are the so-called marginal people, the marginal patients. So in the RCT case, it works out kind of fine. Like the marginal patient here are those compliers, people who comply in either arm, are those who would, you flip the coin, you get assigned to the arm. Treatment, you take the drug, control, you get the placebo. This causal effect is valid for them. Under certain assumptions, it may be valid for everybody, but I don't want to go into, I'm not going to go into that now. I don't want to get too far deep. Yeah, Stan.
In the RCT example, you're going to try to use randomization as the instrument, and you think there's like one-sided non-compliance. Does the non-compliance have to be total? So like, say somebody got like a week's worth of treatment and then like failed. This doesn't really, you can't tease out, partial treatment.
Yeah, so I'm talking about non-compliance being, well, I mean, I guess it doesn't even matter though, right? I mean, like, the point is, what? You have to be able to measure it. So maybe maybe instead of treatment versus control, being like either you got the treatment or you didn't get the treatment. Maybe it's a fractional kind of response. Like you got 98% of the treatment versus 0% of the treatment. If that's true, you could kind of grade it, I think, in a way that's monotonic and meaningful, then I think you could use this approach. But it sounds like you have a specific example in mind. And,
well, no, it's just in like, phase 3 trials in cancer care all the time. I mean, patients, like, the treatment was too intense, and so, like, halfway through, like, 30% of patients couldn't go on, and so then there's the question of whether, the results should be interpreted as, well, we actually need that extra little bit anyways because the patients did better with just half the treatment.
Right. So I think like that's a nice scenario where you've got everyone starts with a treatment, and then it's a simple question of how many, like if there are 10 treatments, 10 fractions, how many of the fractions did you get? You could get anywhere from 10% to 100%, or 0% to 100%, and stack it up, and then your treatment variable is a percentage of treatments. And I think
constructed that way.
well, off the top responses, I don't see why you can't use the same thing as to like you're getting an instrument for whether you got any of the treatments versus none of the treatments, and that's going to be correlated with some positive correlated with the 10% to 100% set. Sorry.
Could you talk about that term endogenous regressor?
So endogeneity basically, the short answer is endogeneity is any of these cases meant to represent any of these cases where we have omitted variables bias, reverse causality, or measurement error. What it means in words, I guess, is that the variable is determined within the system. So we've got this conceptual model, right, of treatment affecting outcomes, maybe outcomes affecting treatment, maybe there's confounders affect. So the treatment choice maybe, if it's endogenous, is affected by the system. It's not simply that it's assigned exogenously from outside the system, but rather that they're sort of patients or people, and they're making decisions. I was assigned to this, but I'm choosing not to take it, so I'm within the system choosing to deviate from the assigned treatment protocol and kind of fall into the control group as a result, the non-treated group as a result. But the sort of, at its basic, it's just endogenous means it's in the conceptual framework, it's in the system, it's in the contained, say 5 times over, it's in the system. Exogenous means it's from outside the system, it's not affected by anything inside the system. An instrument is, by presumption, exogenous. It's not, nothing in the system is affecting it. Nothing in the system, like, this would not be true if we thought where people live is a function of, relative to the hospitals, is a function of their health status. If that's true, and that may be true in the rural, urban context, right, then it's not exogenous anymore. It's being affected by something from within the system, and it's not a valid instrument. Does that answer the question? Kind of.
Sorry. Just with the regressor, like.
Yeah, so that's the treatment status.
Okay.
So think of treatment status as being something that, if it's something that you're assigned to and you can't deviate, it's exogenous. If it's something that you as a patient can deviate from, or you as an actor in the system can choose to whether you're going to comply or not, then there's something else going on that's influencing your decision. It's not happening at random, right? I mean, maybe I don't want the radiation's too much, I can't handle it. That's something about me is influencing my decision to bail out of treatment and go.
The predictor variable of interest, like the one that you care about, the one that's in that. Yeah, the predictor variable. That's what you mean by regressor, I think. Just the predictor variable of interest that you're trying to take other things away from.
Well, I mean, yeah, regressor is X, right? So
yeah, it's X.
Right. Good. Okay. All right. So this walled IV setup this simple kind of instrument variable setup that we use that I applied in the context of a randomized control trial can be extrapolated and expanded to include any sort of instrument variable setup generically, right? So let me just walk through this and think, if it seems confusing, realize it's the same thing as the setup in the randomized control trial. So we have some outcome of interest Y, some treatment variable T, and some instrument for T, which we're labeling Z. But we've also got potentially other regressors W. In a random assignment context, we don't care about the other regressors, or maybe we do, but supposing we don't, they just fall away, right? So this walled IV estimator is the same thing as what we had. What's the mean of the outcome as a function of the value of the binary instrument? So live far from treatment minus the mean of the outcome from those who live close to the treatment. But that's not perfect, so we need to control for what we call in the context of the RCT, the non-compliance. This is where T is the treatment. This is now, did you get the treatment or not? The mean rate of getting the treatment for people who are far from the hospital, minus the mean rate of treatment for those who are close to the hospital. This is a valid IV estimator as long as one key assumption holds. That is, that the other regressors, that is the confounders, are equal across the two groups. If that is true, that is, if there's no difference in our confounders based on whether or not you live close to the hospital or far from the hospital, then this simple formula right here holds as an estimate of the treatment effect, even though we're not controlling for any of the other regressors. We don't need to by assumption, because by assumption, they're equal across groups. And if you can do this, then all the other stuff, I mean, not if you can do it, but if this holds up for your data, then all the other stuff, which can get actually really complicated, all the other mechanics of estimating an instrumental variables analysis, it's I don't say it's icing on the cake, but this is a pretty good basic story here. If you can meet this goal, if you can show an effect here, and you're saying, okay, look, I have to have a binary instrument to make this work, but you can take any continuous instrument, presumably, and cut it up into a binary one. Say, okay, let me just compare outcomes between those far away from outcomes between those who are close by, treatment rate far away minus treatment rate close by. As long as the W's are not different by whether you live far or close to the hospital, you've got an instrument. You've got an instrumental variables analysis. If they don't, then you can actually make this more complicated, like we'll do on Thursday, and control for those other W's, those other confounders that might be not balanced across the far and near instrument thing, or treatment control random assignment thing, and still use the instrumental variable technique. But if you get this is the heart of the instrumental variable approach.
So is the challenge identifying a legitimate instrumental variable? Because otherwise it seems like everyone would do this for secondary data analysis.
Right. Yes.
Okay.
So I mean, yeah,
it's just hard to find it.
It's hard to find one that's credible.
That's credible.
That can pass the sniff test at random assignment is great.
Right.
But if you have random assignment, then you've got a trial. And you're like, wait a second, I'm chasing my